Hello, I'm Jungi from Purdue University. In this video, I'm going to present my recent study, Unbounded Hardware Transactional Memory for Hybrid DRAM NVM Memory System. This work is done with myself and my colleague Jae-Wan Hong at KAIST, and Professor Chang Hee-jung at Purdue, and Professor Sung-Ryul Meng and Young-Jin Kwon at KAIST. Persistent memory is here. It has large capacity than DRAM, while retaining data across power on and off. At the same time, it leverages byte addressability through load store instruction. In-memory database systems and key value stores are already adopting this technology to improve its performance by replacing SSD and reducing power consumption by replacing DRAM. To leverage PM's features such as byte addressability and persistency, persistent memory programming will be prominent. In this slide, let me explain what is persistent memory programming and what it requires. Let's take a look at an example of persistent hash table. It is often used in database systems and key value stores. If there is one thread attempting to add new node to the hash table, the insertion should be done in atomic and durable way. By meaning atomicity, execution has to be done all or nothing based manner. At the same time, modification should be written to NVM for durability. In addition, what if there is another thread trying to insert a new node to hash table simultaneously? If they are conflicting accesses, execution should be serialized, which requires isolation between threads. As a result of atomicity, durability, and isolation, data structure should be consistent at all times. Consistency is app-dependent, so in this example, the persistent hash table must be always consistent state, even if concurrent updates. Therefore, persistent memory programming requires ACID properties, where durable transactions has been proposed. In this study, we leverage hardware transactional memory, HTM, to support durable transaction. ACID properties are not independent, but correlate each other. For example, isolation, atomicity, and durability provide consistency. To guarantee isolation and atomicity, this study used HTM, such as Intel's RTM. HTM is responsible for detecting data races at runtime and serializing them as needed. On the other hand, atomicity and durability are guaranteed by hardware logging techniques. They are responsible for flushing data to NVM and managing the persist order. So combining the HTM and hardware logging approaches provide durable HTM, which is target of this paper. And the basic idea of durable HTM is already proposed in the previous study, but we identify drawbacks, as I'm going to explain soon. The first limitation is that it only supports NVM data in a transaction, while on answering how to manage interdependencies between DRAM and NVM objects. According to the recent trend in persistent memory programming, they pursue to use both DRAM and NVM data in a transaction. For example, recent proposals for persistent key value stores place the index structure in DRAM while storing data in NVM. So this design accelerates the search operation since the index is in DRAM. However, it complicates the case of insertion, where both DRAM and NVM should be modified in an atomic way. If the programming model doesn't allow manipulating both objects in a transaction, it is extremely difficult to manipulate them in an atomic way. Therefore, not only exploring the fast DRAM speed, there is another reason to call for supporting hybrid memory, which is to simplify programming. To this end, we have compelling need to support hybrid memory, hybrid DRAM NVM transaction. The second limitation is its boundary. Commercial HTMs only allow speculative data to place in L1 cache, supporting transactions that exceeding this boundary. Furthermore, even if the state-of-the-art durable transaction, durable HTM extends the boundary to LLC by modifying the cache coherence protocol, it bounds in the on-chip cache size, since the cache coherence only works within the cache boundary. Unfortunately, LLS is not a safeguard. Persistent application tends to increase their data size, and virtualized environments exacerbates contention in LLC, which can lead to cache overflow. The transaction boundary matters, since if a transaction exceeds its boundary, then it has to abort since the HTM no longer supports correctness. That is, programmer should reason about the size of transaction, not to overflow the limitation. The practical HTM programming convention recommends to implement the fallback path that the overflow the transaction should execute. However, this practice not only increases programming difficulty, but also decreases concurrency by serializing transaction. On the other hand, previous unbounded HTMs consider DRAM-only system, so they are not satisfying the durability property. Also, they incorporated the address signature to capture conflict, ended up being suffered from very high conflict rate due to false positive. Therefore, durable HTM should be able to detect conflict at all memory hierarchies with low positive rate. To this end, we proposed unbounded HTM for hybrid DRAM memory system. Our system is called UHTM. It has the following two key features. First, it should be able to detect conflict in any memory location, including both on-chip caches and off-chip memory. Second, UHTM should manipulate DRAM and NVM data in a transaction and recover them consistently in case of abort or power failure. The challenge of achieving the first goal is the very high false positive rate of signature. We observed that more than 90% of transactions conflicted due to the false positive in the L1 cache signature, ended up serializing them for all the progress. So we should reduce the false positive rate to provide efficient durable transaction. The key idea of UHTM is to stage detection scheme based on the memory hierarchy. For example, within on-chip caches, since they are frequently accessed, we need a technique that is accurate. However, for off-chip memory, it is okay to be less accurate since they are less frequently accessed, allowing false positives, but it should be unbounded. Based on the previous design goal, UHTM presents a staged conflict detection that uses cache coherence protocol for data in on-chip caches. It extends the directory-based coherence to detect conflict. And it also leverages address signature for off-chip memories, which can detect data conflict without limitation. Since the address signatures only record overflowed blocks, it has much less chance to produce false positive. By having different detection scheme, UHTM reduced the false positive rate from 90% in the signature-only system to 26% when we only use 512-bit signature. But still, we have a quite high false positive rate. Can you reduce it further? Of course, having a larger signature, such as 16K bit, helps reducing the false positive to 9%. However, if we consider signatures are per core structure, large signatures will have space overhead. Other than increasing the size of signature, UHTM presents an alternative solution based on the following observations. First, we observed that false conflicts not only between transactions, but also between transactional and non-transactional processes. For example, durable transaction abort due to false conflict with the background processes that have no data sharing. That is, there is a possible conflict, but address signature generates a false positive. On the same extent, the number of cores or the number of signatures determine how vulnerable to false conflict, false positives. In other words, we need to exclude the signatures of different processes from the conflict checking. So to this end, UHTM presents signature isolation technique. We first define the conflict domain, which is the group of transactions that potentially have conflict with each other. Therefore, conflict checking happens only within a group. It's already in the same process with this example. Initially, each process has a unique group ID, and whenever a new thread is spawned, the thread inherits the same group ID by default. Since the conflict domain confines signatures participating to the conflict checking, the possibility of false positive decreases. The signature isolation technique is particularly beneficial in a virtualized or containerized environments, where durable transactions are consolidated with other processes. In addition to UHTM's unlimited complexity detection, it also supports hybrid DRAM NVM data. In other words, UHTM guarantees atomicity of DRAM NVM data and durability of NVM. UHTM provides hardware logging techniques to support atomicity. Since commit is more common than aborts and crashes, we optimize UHTM's logging technique to minimize the commit latency. To this end, UHTM presents hybrid logging approach, which use underlogging for DRAM data and with-logging for NVM data. While the commit of DRAM data completes fast with the eagle approach, which overrides data in place within the transaction, NVM commit becomes faster with the lazy approach, since it places the costly cache flush to the outer critical path. And also, UHTM guarantees durability and cross consistency with NVM redo logging. This is our methodology. We used the Zen5 simulator to evaluate UHTM. All experiments were performed within 16-core configuration, and we evaluate UHTM with the state-of-the-art durable HTM. That is LS-bound and signature-only HTM. We also compare UHTM with the ideal unbounded HTM that has no false positives in the conflict detection. Throughput are normalized to the LS-bounded HTM. First of all, I would like to explain how much the ideal unbounded HTM are performed in the LS-bounded one, which demonstrates the need for unboundedness. In benchmarks such as bit3 and RB3 and skip list, the ideal HTM shows substantially higher throughput than the baseline, showing 8.2x throughput in bit3. On the other hand, signature-only bound HTM even shows lower throughput than the baseline. This is because signature-only system turns out to generate too many false positives, so that transactions were highly serialized. However, UHTM drastically reduces the number of false positives, making UHTM highly outperform the baseline. Furthermore, UHTM achieved throughput close to the ideal except skip list with the signature isolation technique. For more experiments, please refer to the paper. Let me conclude this talk. In this paper, we presented UHTM, unbounded HTM for hybrid NVM memory system. UHTM has two design goals: unlimited complete detection and hybrid transaction support. To do so, we first presented staged complete detection that used cache coherence for data in on-chip caches and address signatures for off-chip memory data. This combination leads to lower false positive rate, which was the key challenge of this goal. Next, UHTM provides hybrid logging for DRAM and NVM data to minimize commit latency. Thank you for watching this video, and if you have any questions, please join the session 5A, Hybrid Memory. Thank you.